Namaskar, I am Neha Tripathi. We are here with our special session, the webinar on ICT tools. These times have given us the opportunity to explore our capabilities and made us learn new tools, manage our work and be creative at the same time. Every day NCERT brings to you an innovative tool. We have dedicated this week to tools related to mathematics. Today we are here to learn about Geogebra. We already had a couple of sessions on its applications in mathematics. Today we will understand its application, that is the application of Geogebra in other branches as well. To help us explore this platform, we have with us Mr. Sukesh A. He is Assistant Professor in Government College of Engineering in Kannur, Kerala. Welcome to the show, Mr. Sukesh.
Thank you, Neha ma'am. Thanks so much. And I'm indeed very happy to be with you, dear viewers, in this special occasion.
Yeah, we'll come to you, sir, in a couple of seconds, in a minute or so. Before we start our conversation for the day, here I want to add that if you have any questions related to this topic, you can call us on our toll-free numbers 1-800-111-265 and 1-800-112-199. If you want to mail us your queries, mail us at ciet.kishoremanch@gmail.com. And if you are watching us on our official YouTube channel, NCERT Official, you can get back to us in the comment section as well. So let's begin the session and we will take up your questions at the end of the session. So keep posting us. Mr. Sukesh, we have known Geogebra for mathematics and we have explored it in 2D as well as in the 3D platforms. Today you are going to explain us how its applications in other branches. So we can go ahead with the demonstration now.
Yeah. So hope you have all gone through the 2D Geogebra session by Madhu and 3D Geogebra session by Ramanujam. So this is in fact a deviation from that. There we were actually concentrating on mathematics. Here we'll concentrate on how we can use this application to demonstrate other ideas in other branches. So I have a couple of ready-made applets with me. I won't be going through the construction process. Now, before making use of Geogebra, I mean, if you decide to use Geogebra in your application or whatever in your teaching process, please bear in mind two things. One is that whenever you're using Geogebra, the emphasis should be on the content rather than Geogebra. Geogebra should stand back and your content should stand front. So that is the way the teaching should go. And the second one is that if at all you feel that using this ICT tool is very essential, then only use it. Otherwise, please don't try to use, I mean, for simple cases where where the idea is very easily understandable, don't use Geogebra. This can be used for making more clarity in ideas. So I'll start with physics. So this application applet is related to projectile motion. So you can see in the screen, I hope you can see the screen. Here, suppose I'm launching a rocket or a missile or something from this particular point. We call it as the origin. Okay, I'm launching it with a velocity of u0 along with making an angle of maybe alpha. Okay, with the x-axis. So from vector algebra, what I know is that this vector can be resolved into two parts. One is the vector along the x-axis and the other is a vector along the y-axis. Along the x-axis, you will have u0 cos alpha, and along the y-axis, you have u0 sin alpha. Okay. Now, suppose I want to know how far this is going at a particular time t. Then what I need to do is, if I know the velocity, simply multiply with time, I'll get the position. Okay. So what we can do is this u0 cos alpha, if I multiply with t, I'll get the x component. Similarly, in the y direction, I know that my velocity is u0 sin alpha. So I'll multiply with t. But there, an extra complication is there because Earth is pulling this body downwards. Okay. So we need to account for that also. So we'll have a term minus half gt square along with this. So what I've done here is, for this point, I've given the x coordinate as this value and y coordinate of this value. Now let's see what happens if I animate this. See, if I animate this, you can see that initially the object goes along u0, then after some time it starts coming down. So it deviates from its path and it starts coming down. Okay. Now what happens if I change the angle? Maybe from 59, I'll change it to some other angle. Okay, maybe 40, 37 or so. Now, now if I do this, what happens? See, again, you can see that the body is starting along the along U0, and then it is starting to deviate. Okay, now this is also valid for other velocities as well. Okay, suppose I'm increasing the velocity maybe to something else, and then if I launch this this particle again, you can see that here also it starts along and then it goes in a different path. So whenever I'm changing the velocity or whenever I'm changing the angle, it goes in a different path. That is fine, but you can see that the shape of the path is almost in a projectile form, okay, or in a parabolic form. Now, this is valid only even if you put the angle as 0. If I put the angle as 0, you can see that, see, initially it goes like this horizontally and then it comes down. Again, it is in a parabolic fashion. So one takeaway message from this applet is, okay, now I have understood that the path is parabolic, so I have kept the parabola here. Okay, you can see that for different velocities, I'll have different parabolic paths, and for different angles, I'll have different parabolic paths. Okay, now we'll try to concentrate on a particular point called the range. You can see that there is a range written here, 11.64. Actually, range is the distance from the launch point to the strike point. The strike point is here. Okay, the distance from this point to this point is called the range. Now, suppose I want to know how far this object goes if I change the angle. Okay. Now, if I start from a 0 angle, see, it goes, the range starts increasing. Okay. Then after some particular angle, it starts coming back. See, you can see that it starts coming back. Okay. Now, what I want to know is, what is the angle that will reach maximum, or where the range will be maximum. Okay, so for that, what I can do is I can please look at the values of the range here. So for higher values of angle, the range is small. For lower values of angle also, the range is small. Okay, so at 45 degrees, you can get the maximum range. Okay, this can be demonstrated in another fashion also. That is, suppose I'm trying to, this is my maximum height point. That is during the path, I'll reach the maximum height here. Okay, so suppose I'm trying to see what is the locus of this angle. You can see that the angle is increasing, and then the path, it actually traverses a parabolic path. You can see that it turns back again. Okay, now you can see that it draws the parabola there. Okay, now what is the maximum point of that parabola? So this is something like a graph is overlapped on top of the path, projectile path. So you can see that the maximum point is obtained here, and that is 45 degrees. Okay, so this is the way you can demonstrate this. Another direction that you can go is, see, I have a target here. This is a mobile tower, and I want to strike this mobile tower. Okay, now I know that the best possible angle is 45 degrees. So I'll keep my angle as 45 degrees. And now I want to increase the velocity so that I'll reach here at this particular target. So if you see that if you increase the velocity, see, it goes and strikes there. Oh. Okay, so this is the velocity required. That is 14.6 is the velocity required to strike this particular object. So you can actually change this position of this target and all. And if you give this to students, they can explore a lot on how what are the values of this velocity and things like that. Another direction that we can go is regarding this range and maximum height. You can see two numbers here. One is the range and one is the maximum height. The range is the distance from this point to this point, and the maximum height is the maximum height that the object travels. Okay. Now, what is the relationship between these two? We'll go to some convenient numbers, maybe 20 or so. Okay. So you can see that at about 20, you can see that the value of maximum height is 5. So what is the relationship between this? 5 is actually 1/4 the range. Okay, so this can be explored. This is also true for other values also. Every value, whatever value you take, you can see that it is always 1/4 the range. That is at this particular angle, 45 degrees. Now, one more direction that we can take this applet is that suppose I'm changing the acceleration due to gravity. Okay, acceleration due to gravity is obviously a fixed quantity, but suppose you are in the moon, okay, and you want to launch this vehicle or the rocket. Okay, in the moon, I know that the acceleration due to gravity is 1/6 that of the acceleration due to gravity at Earth. Okay, so obviously in the moon you can't see this beautiful landscape, you can't see this sky and all. So I'll keep 45 degrees. Now, if I want to strike the same mobile tower, if I'm fixing that mobile tower in the moon, okay. Now you can see that yeah, okay, yeah. So the value is about 6. Okay, so at a value of about 6, we can actually strike the mobile tower. Okay, so this is one way we can teach projectile motion using this applet. Okay, now we'll go to a different topic from here. This is geography. Okay, in from mathematics, that is coordinate geometry, what I know is if I want to fix a point on the surface of a plane, or on the surface, what I need is I need 4 parameters. Okay, one is the x coordinate, that is the distance along the x-axis. One is the y coordinate, distance along the y-axis, and then I need the x-axis and I need the y-axis. So 4 things are required. Okay. Now, what happens if you want to do it on the surface of the Earth? Okay, so you need obviously 2 axes and 2 parameters. So the first axis is actually the equator. Okay, now if you see, this equator is a circle which actually divides the Earth's sphere into 2 pieces. One is the upper hemisphere and the other is the lower hemisphere. Okay, upper hemisphere we call it as the northern hemisphere, and the lower one we call it as the southern hemisphere. Now, we have a concept of latitude. Now, what do you mean by latitude? We draw some circles. Okay, these circles can be drawn with the same axis as that of the equator. So you can go up, you can go down. Okay, now this circle is called the latitude circle. So whatever point you want to mark, you draw a circle there. Now, if you want to specify this circle, say for example, if you want to say 30 degrees, okay, the degrees is the, line joining this circle to the center of the Earth and the equatorial plane. Okay, now if you say 30 degrees, you can say that this latitude has 30 degrees. Now, there is an extra problem there, that if you go below the equator also, you will get 30 degrees. Okay. So it means that you have the 2 latitudes for 30 degrees. So you want to distinguish between these 2. Then what you need to say is, you need to say whether it is in the up or whether it is in the lower one. So you need to say whether it is in the north or whether it is in the south. Okay. So that is how latitudes can be defined. Now is the longitude. Longitude is, again, it is a circle that is drawn on top of the Earth. Okay, connecting the 2 poles, that is the north pole and the south pole. You connect the 2 poles and you draw circles. Now you can see that 2 poles can be connected in different circles. See, there are many possible values, but you need an axis, right? So if you need an axis, the question is what place will you put this longitude for that axis? Okay, so this was a long debating problem, and finally they fixed the longitude as the prime meridian, which is passing through Greenwich. So if you explain this in terms of geometry, there should be 3 points on a circle to make the circle a unique circle. Okay, one is obviously the North Pole, the other is the South Pole, and you want one more point. Then only you can fix a circle. Okay, so that is passing through Greenwich. That is how this longitude is defined. Okay, and the value of longitude also, it is given by the angle from this prime meridian. Okay, the angle is specified as angle either east or west, because this circle in this portion is the east portion, and the behind the circle, that is the west portion. So that is how longitudes are specified. Now, apart from these, there are some important latitudes. There are latitudes, there are many latitudes, but some latitudes are of prime importance. Okay. To understand that concept, we need to understand what a solstice is. Now, if you see that this Earth, okay, the sun, it starts, the movement of the sun is in a very peculiar fashion. Okay, it starts from this equatorial portion in the March, and it goes up. Okay, goes up and reaches this point in June, and then it comes down. At September, it will come down again here, and then it goes down. It goes down, and December you can see the sun here, and then it comes back. Okay, that is how the motion of the sun is. We call this top point as the summer solstice, and we call this bottom point as the winter solstice. And the central point, we call it as the equinox. Okay, so there will be 2 equinoxes, one in March, then it goes up and comes down again in September. So 2 times you will have this equinox there. Now, this you can do in, this can be modeled in 2 ways. Okay, one is that you can make the sun as a fixed value and then change the earth, or you can change the sun and you can keep the earth fixed. Okay, so before that, we'll see that this point, that is the summer solstice point, is defined by the Tropic of Cancer. Okay, this is the Tropic of Cancer. This is up to this point, the sun will go. Okay, and you have a similar circle below where the sun will go in the winter solstice, it will go up to Tropic of Capricorn. So you have 2 circles here. Okay, so as I said, you can either keep the sun fixed and move the earth, or you can keep the earth fixed and move the sun. Both are the same. So what we'll do here is we'll actually keep the sun fixed. Okay, so in this applet, you can see that this yellow portion is the rays from the sun. Okay, it is fixed. And what I'm doing here is for this earth, I'm tilting the value. See, I can tilt the earth here. Okay, now I can tilt the earth from minus 23.5 degrees, that is the value of the Tropic of Cancer and Tropic of Capricorn, to plus 23.5 degrees. Okay, this is how I can tilt the earth. Now, let's see what happens if I mark 2 points on top of the earth. Okay, so I'm marking 2 points. So you can see that the point on the earth is marked. See, there is a red marking on top of this. Here in the equatorial region is also there is a red marking that indicates a place. Now, when this starts rotating, you can see that half of the time, the equatorial region, half of the time it is going inside the influence of the sun, and half of the time it is outside. So whenever it is going inside, you have daytime, and whenever it is out of the influence of the sun, it is nighttime. Okay, so you can see that the point is moving. Okay, now it is nighttime for this particular point. Now, what about the point on near the pole? You can see that at this position, the point on top of the, near the pole, it is always in darkness. It never goes in the influence of the sun at this particular angle. Now, if you tilt this from this point to maybe 23.5 inside, okay, you can see that whatever be that point is always under the influence of the sun. Means that in 24-hour duration, you get sun there. And some other points, the opposite points will always get 24 hours of darkness. Okay, this phenomenon is called the midnight sun. So it is observed near the polar region. So midnight sun is you can see sun in the midnight also there. That is the idea. Okay, so we will keep it here. Now, that is the concept of the midnight sun. Now, coming back to our old applet, you can see that whatever place is coming under the which is experiencing midnight sun is called the Arctic Circle. Okay, and whatever place experiences midnight sun in the below, that is in the southern hemisphere, you call it as the Antarctic Circle. So these are the prime circles of importance related to the Earth. Now, using this applet, I can also demonstrate solar eclipses. Okay. Now, suppose I am trying to model the sun. The moon also. See, now the moon is rotating around the Earth. Okay. Now, when the moon is rotating around the Earth and it comes under the influence of the sun, okay, in between the sun, okay, there you can the moon blocks the sunlight from whenever the light is coming from the sun, moon blocks it. So this can be demonstrated using this applet. Now let me just show you how the shadow will come. Okay, so I'm keeping the moon in between the sun and the Earth. Now see, I have the shadow of the moon now. See, wherever this shadow comes, okay, when the shadow comes, whatever place is under the shadow, it will experience a solar eclipse. See, this red point, it will go inside the shadow and then it will experience it. You can see it from this view also. Okay, I'll show it from here. The sun is, I'm standing on the sun. Now I can see the moon here and I can see the Earth. See, this point is coming under the inside this shadow. There, that particular place will experience solar eclipse. Okay, so this is how I can demonstrate eclipses. Okay, now I'll just close this applet because I mean many applets opening, it takes a lot of heavy CPU space. Okay, so I'll just open the others. Now the next applet that we are going to look at is related to waves. Okay, now I'll show you. Waves is normally a very difficult topic as far as physics is concerned. Okay, so see here, I have this applet. There are two waves I've modeled. A wave is mathematically represented as A sine omega t minus kx. This A is called the amplitude, and this omega is called the frequency, t is the time, k is the scaling factor. Okay, now let's see what this wave looks like. See, this wave, you can see it in green here. Okay, so this is a wave represented by A sine omega t minus kx. Now as time goes forward, what will happen to this wave? Look at the way in which this wave is moving. See, the wave moves in the positive direction, that is rightwards. Okay, now suppose I'm changing this equation a little bit, and I'm saying instead of A sine omega t minus kx, I'm saying A sine omega t plus kx. Now see what happens. The wave starts moving towards the left. So by just changing this minus to plus, you can make a traveling wave which moves in the negative direction. Okay. Now what if I combine these two waves? Okay, so I can see that wave 1, it goes in the positive direction, wave 2 goes in the negative direction, and you can see how beautifully it comes up. Okay, now suppose I want to combine these two waves. Okay, if I want to combine these two waves, I'll just simply add these two waves together and I'll get something called as a standing wave. Now to experience this standing wave, I'll just switch off the other waves. Okay. Now you can see this wave, it is not going anywhere. It is not going towards the right or it's not going towards the left. It's just oscillating from that place. Okay. These waves are called standing waves. So standing waves are normally, we teach it using pure mathematics, but it can be taught using this in a very nice way also. Now we have a different kind of wave which we call as the longitudinal wave. Okay, in the longitudinal wave, again, if I show you a longitudinal wave here, okay, I'll show how this motion happens. See, this wave, it starts going in the positive direction. Okay, this is a longitudinal wave. It's a sound wave is an example of this longitudinal wave. Okay, now what about the wave in the towards the negative direction? See, this is a wave towards the negative direction. Again, you can see that these are actually compressions. Okay, compressions are going towards the left in this case. Now, what will happen for the standing wave? Standing wave is a beautiful thing to look at. See, the standing wave, when these two waves are added together, you get the standing wave. It's very, curiously, it actually compresses a lot and then expands a lot and again compresses a lot and stays there. Okay, so this is one example of waves that we can explore. Now this can be extended to music also. Okay,
Wow.
now I'll show you some music generated by waves. Okay.
So meanwhile, there is a common
Yeah.
question from our viewers. They're asking if these, whatever you're doing on GeoGebra, this is a 2D thing or a 3D thing?
It is both 2D. This is actually 2D.
Okay.
The Earth I showed you is 3D.
It was 3D. Okay, it is a mix.
Yeah, it is a
Just
mix.
let us know which one is 2D and which one is 3D.
Okay. This is a 2D applet. Okay. So here you can see that I have two waves. One is the red one with a frequency of 1. Okay. And the green one with a frequency of 2. Okay. Now you can see the combination here. The combination is a blue one. Now I'll just, I'm not sure whether you can hear the sound. It is a low frequency is very difficult to hear. I'll increase the frequency a little bit. Okay, I'll make it as 250. So this is, a little bit. It will be some difficulties will be there while hearing it. To be a kind of an awkward kind of a sound. Okay.
Yes,
I'll
we
put
can
this-
even see the waves, they are broadened up.
Yeah, right. I'll put it as 251. Okay. Now I'll play 250, a frequency of 250. Okay. Can you hear? Did you hear it?
Yes, sir. We could.
Yeah. Now 251, I'll show you. Okay. It
Yes.
seems almost the same, right?
Yes.
Now I'll show you the combination 250 plus 251. Okay. You can see a ambulance kind of a sound there. So if I increase that to maybe 254 or something, okay. Now, see, this phenomena is called beats. Okay, this is actually a beats of 4. The difference between 250 and 254, it creates a 4-beat sound. Okay, what you heard was a 4-beat sound. So if you want, you can play around with this with different kinds of frequencies. This is also called and this is a 3-beat sound.
Okay.
So that is how you can generate sounds. Now there is a very interesting factor here. Suppose I put this as 500. Okay. Now you can see that 250 is the basic frequency, and the other one is of 500, which is 2 times. Okay, an integral multiple. Now let's hear 250. Let's hear 500. Okay. Now let's hear the combination. You can't make out between the combination and the 250 basic frequency. Okay, both almost are same. Now there is a special application in your mobile phone which we call as the pitch analyzer. Okay.
Yes.
If you install the pitch analyzer and analyze the sound for the combination, it will be giving us 250 only. Okay, so it means that 250 and 500 are indistinguishable in terms of the combination. Okay, so these kind of sounds are called harmonic sounds. Okay, So that is the concept of harmonic sounds. You can make them experience. But the main difference is that if you look at the amplitudes will be more for the combination rather than the bass sounds. Okay. So this is one place where we can make use of applets. Now I'll just close this and I'll go to the next session. I'm sorry because I have to close this because it takes a lot of CPU space.
No problem, sir. We are, going through each applet one by one and understanding them clearly.
Okay.
Please go ahead.
Now I'll show you how AC current is used. You always get a sine wave, right? So let's see how this AC generation happens. Now to go into that, suppose that I have a rectangular plate. Okay, it is there situated in a place where water is flowing, water or some fluid. So this blue one is water. Okay. Now my question is, how much water will be flowing through this, rectangular plate? Mm-hmm. So if you place this rectangular plate here, you can see that maximum water will go through it. Now, if I change the orientation a little bit, okay, and I keep this here, okay, how much water will flow through this? You can say that what I mean is that water is flowing through this cross section. Okay. Mm-hmm. Now water is not flowing through this cross section in this case. Now here if I put, I'll get maximum water flowing. So I want to model this, and I want some number which could be used for multiplying this particular area. Okay. That number should have 1 in this position, and it should have 0 in this position. Okay. Now one such and before that, now area, this rectangular plate has an area, right? In physics normally we have this concept of vectors and scalars. Okay. Now regarding in some places we use area as a vector, in some places we use area as a scalar. Some places we'll use distance as a vector, and some places we'll use distance as a scalar. Now, where do you scalars? Okay. Now, in this case, when I change this area, since the amount of water flowing is different, it means that direction is important. Okay. So I'll have to use this area as a vector. That is why this vector direction is there. Okay, it is perpendicular to that area. Okay. Now let me show you how this area will, how much water will flow through this area. Okay. Now if you see in this side, I have a red point here, right? Now I'll change the orientation, and you can see that the red point is changing. So I want maximum water here, and when I come to this point, I want 0 water to pass. Okay. And if I go in the other direction, it should go in the negative direction, since it is a vector. This kind of a shape. An obvious choice is cos theta. Okay, so cos theta will have 1 at this particular point and 0 at 90 degrees. Okay, and then it will go down. So this is the amount of water. Now let's forget this water for the time being. There is no water. Okay, now here instead of water, let's assume that this is a place filled with magnetic field. Okay. Same concept. Instead of water, we are saying here there is some magnetic lines of force or something like that. Some magnetism is flowing here. Now, flowing is from this point to this point. Okay. So when it flows from this point to this point, obviously there should be some magnet that is creating it. Okay. So I'll put a magnet here. This red one is a north pole, and the violet one is a south pole. So the magnetic lines start from this point and it goes towards this point. Okay. Now what happens when I change this rectangular plate inside? Instead of water, what I'll say that magnetic field this, it goes down and then it comes up like that. Okay. Now, suppose I want to see how this change, okay, will affect a conductor. If I'm placing some conductor, suppose I'm placing a wire here, okay, around that rectangular plate. Okay, I'm placing a wire which goes, wire in the sense a conductor which is wound in the form of a rectangular shape. Now, if I move this, what happens? The flux is changing. Okay. Now, here comes Faraday's law. Faraday demonstrated that if you rotate this, a voltage is developed between these 2 points, between these two conductors. So, when the voltage is developed between those two conductors, and Faraday also showed that if you if you rotate this with a higher speed, okay, more speed, more voltage you get. Okay, so when you rotate it, you get voltage. When you rotate it faster, you get more voltage. This is what Faraday showed in his experiment. So let's see how that voltage will look like. Okay, and one more thing that Faraday said was when the voltage is, he said that, see, when obviously if you are changing this flux, voltage is coming up. Okay, now voltage is equal to the rate of change of flux. That is what he said. So if this red one is flux, then it means that the derivative of this red one should be voltage. Okay, now let's see how that voltage develops. See, here I have a green shape which gives the voltage developed across this coil. Okay, so that is how AC is generated, and you can see that the AC obviously shows a sine wave. Okay, now suppose I'm increasing, okay, the speed. Now what will happen? Let's see. I'm putting it about 2 or so, and I have increased the speed now. Let's see what happens. Increased. Okay, now I'll just increase the speed a little bit more. Okay, I'll increase the speed a little bit more. See, again, more voltage is coming. So as you increase the speed, you get more and more voltage. So if you want to get more voltage, you simply increase the speed here. So this is the idea behind AC power generation. Okay, so this is one applet that we have for AC. Now you can also use Geogebra to teach these continents. Okay. Now this Geogebra applet, this I have not created this applet. I have downloaded from a source which we call as geogebra.org. In geogebra.org, you will have thousands of applets are there. This is a beautiful applet that shows the longitudes. See,
sir, even our viewers can download these applets.
Right.
Do brief them. Yes, sir. Do brief them about this also, how they can go and download.
There are different sources for making GeoGebra applets. One is you make your own GeoGebra applets. Whatever I have showed before this, everything that I have created. Okay. So those, I mean, you need to have a hands-on experience on GeoGebra to do that. For the first thing. So first you need to study GeoGebra to make whatever applets you have. But if you are in a hurry, you don't want to study this, but you want to use it, then you have an option of going to a site called geogebra.org. In geogebra.org, you have all kinds of applets, okay, which can be downloaded and used for academic purposes. But the only thing is that you need to credit them. You need to say that, see, I have downloaded this from this site.
Of course.
Okay.
Yes, sir.
Yeah. So that is why I am saying that I have not created this. I have downloaded this from. So here you can see visualize continents. Okay. All the whole globe you can use here for demonstrating the continents and how this whole thing comes up. So I can also show you one example where this particular, this is also from the same source which I downloaded from geogebra.org. Okay. I'll show you how this can be used for demonstrating the equinoxes that I've told you about earlier. Okay.
Yes, sir.
Yeah. See, this is the source. This is the Earth, okay, with all the continents marked. And I told you that in March, near the equator, we can see the, sun, right? So this is the March equinox, means this point. Okay, you can see the sun here as a small circle. Okay, at this particular spot in the globe, you can see sun at directly above your head, making an angle of 0 degrees with the vertical at midnight. 12 o'clock in the afternoon. Okay, so now you can see that in June the sun goes further; it goes up. June the sun goes northward. Okay, the sun was below now, below for in the March, and in September it comes down. Okay, yeah, September it comes down to the middle of the earth. Then in December it goes below. See, it has gone below.
Yes.
Okay, so these motions can be, you can see that it just at December it crosses this red line. Red line is actually Tropic of Capricorn.
Yes.
Okay, it is directly above Tropic of Capricorn here. And in June, you can see it is directly above the Tropic of Cancer. Yeah,
yes, sir.
right. See, it is directly above the Tropic of Cancer. So these applets can be used for, demonstrating some difficult to understand topics. So that is the main emphasis. Okay. So in short, GeoGebra can be used for demonstrating whatever topics you find it as difficult. It can be simply applets can be made, custom made applets can be made, and it can be used for demonstrating this.
So,
Okay. Yeah.
yes, we can go ahead. If you want to add some more, please.
No, if you have any questions, we can take it up. And
I just wanted you to, just do a quick revision of what all subjects you have actually demonstrated using these applets today. If you can just tell the names of the subjects.
Today, first we started with projectile motions, that is related to physics.
Okay.
So there we just saw how this path changes in a parabolic fashion, and then we went on to finding the range of the projectile. We saw the relation between the range and the maximum height attained. We saw how to find the locus of a projectile. I was just hurrying through those applets actually because I wanted to show
all the applets that you understand completely. We don't want to miss anything for telling our viewers. Yes, sir.
So the second one that we demonstrated was the concept of latitude, longitude. How this,
that is, of course, geography.
Geography. Latitude, longitude, and then marking a point on the surface of the earth. And then we also showed you how the solstices, that is the equinox, what we have just told now, equinox and the some places on top of the earth will get half a day of sunlight and half a day of night. Okay. It doesn't get light. It's the midnight sun. Okay, that also we demonstrated, and based on that we said about two more circles which we call as polar circles, that is the Arctic Circle and the Antarctic Circle. Okay. Now after that we saw something about waves. how to combine two waves. First, we talked about traveling waves, waves traveling from one place to another place. So for that, we saw that the waves are moving either in the positive x direction or in the negative x direction,
And
depending on
that is
the.
also related to physics only, sir?
Yeah, that is related to physics.
Yes.
Physics actually acoustics. Okay. Acoustics in physics. So there we saw that by combining two waves, you can have two different. I mean, you can hear beats actually. Okay, so you can have standing waves. Sorry, when you combine two waves, you can have standing waves. That is what we demonstrated using this particular applet. Okay, you have a standing wave. The wave doesn't move. Okay, so the other two waves, that is the small ones move, but the standing ones don't move. Okay, so this was the applet that we demonstrated using waves.
Yes.
Similarly, there is these kind of waves are called transverse waves. It means that they just the particle actually vibrates. Yeah, that you can show. I just forgot to mention that.
Yes, please.
See, suppose I'm showing you this. I'll show you this positive direction wave. Okay. Now, if you see this wave is moving in the positive direction. Okay. Now, if you take a particular point here, maybe at this particular point, now this up and down, that is actually the amplitude. Okay. Now, if you can see that when the zero comes here,
Yeah.
I'll just stop this for a time being. Yeah. When say now I'm considering this particular point here. Now this point has an amplitude of this much. Okay. Now after some time, okay, when this point now this point has an amplitude in the positive direction.
Okay.
It goes up. Now when you see that some points go up, some points come down, go up, come down, go up, come down. It moves like this here, the particle. Okay, so the particle and the direction in which this wave is moving is perpendicular to each other.
Yes.
That is why we call this as transverse wave. Okay. Similarly, we have another kind of wave which we call as the longitudinal wave.
Okay.
In the longitudinal wave, the movement of the particle will be in the same direction as that of the motion. Okay, I'll just show that also. Yeah. So see my first wave. This is the wave. Okay. Now, if I see, if I just animate this, you can see that the wave is moving in this side, right? Positive side. It goes towards the right. Now, if you look at one object here, see, suppose I'm looking at this point number 6. Okay. Here there is one line. Okay, you can see the width here, gap. Now, after some time, you can see that the width has changed there. Okay. Now, after some time, again, you can see that the width has changed. So, what happens is here the particle is vibrating along the direction of the wave. However, the wave is moving, the particle is also moving along the direction of the wave. That is why we call this as longitudinal waves. Sound wave is an example of a longitudinal wave. And ripples in water is an example of a transverse wave, where the particle moves up and down, up and down, up and down. Okay, so that is how these waves are. And in this, we also demonstrated the beats. Beats is actually the combination of two waves. That is very easy to make. The applet is very easy to make. Okay.
Okay.
It is not very difficult. You can do it offhandedly. That is, it's actually a sine wave. If you see what I've demonstrated in front of you is, it's actually a free sine wave with frequency 1. You can see that this green color wave, no, it is having a frequency of 1. Okay, you can see that this green color is having a frequency of 2. Means from this is 0, right? And this is 1, right? In between, you can have two waves. See, 1, 2. Okay, that is the two frequency wave. The red one is a 1 frequency wave. It means that from 0 to 1, you have only one cycle. See, one cycle. Okay, so in this case, we demonstrated the beats. Now beats are you can experiment with this in a very beautiful fashion. See the only one command I've used here is in the play button. Whatever I done here, okay, I have added a particular script. Okay, now I can show you the script if you want. It's just a simple script. See, I have written play sound F01. That's it. Okay, then you get the sound there. Okay, GeoGebra has lot of features for, I mean, lot of features which is very exciting. So sound is one such feature. Okay, you can make some. Now this can be experimented in a different way also. Suppose you want to produce the Saptasuras. Okay.
Okay.
Sarigama Padanisa. Okay.
Wow.
Each sa.
Just want to inform you, sir, we are left with last 4 minutes of the session,
Okay.
but this is going to be interesting if you can explain that in that time.
Yeah, 240 is the frequency for sa. Okay.
Okay.
And for ma, you have 324.
Okay.
324 is ma. In Carnatic music, that is what I'm saying. Okay.
Achha.
So I'll show you sa. Okay, this is a piano sound. Okay, sa. This is ma. Okay. So similarly for every seven this one you have different frequencies. You just need to change that frequency. You can generate a whole lot of sounds there. Okay. In fact, you can even make a piano which has all these keys. When you press the key, you get that particular sound. Okay.
And everything that we are creating here can be shared with our students if the teachers are creating.
Yeah. Obviously, because this is an open source software, GeoGebra. It is freely downloadable. So it means that whatever you are creating here is meant to be given freely.
Of course, but how to do that? If you can just tell our viewers how to share these things.
Yeah, one thing what we can do is if you have created some applets which are really interesting and you want to give you want to share it to the world, GeoGebra is one for platform. Okay, you can create an account in geogebra.org and we call it as GeoGebra Tube, like YouTube. Na? We have GeoGebra Tube. So you just upload your applets there. People all around the world will be using your applets. Similarly, you can use whatever applets they have created for their own purpose. You can download it and use it for your own content delivery. Okay. So that is what I wanted to show you.
Any suggestions for our viewers while using this particular tool? They need to take care of certain things.
Yeah. One thing is focus on content rather than the applet. Okay. Because when you, I mean, if you have a very understandable topic, some obvious things that are very easily understandable, don't use applets for that. Okay, that is really boring because students are better in terms of technology than teachers. Okay. So they'll find it really awkward using those silly applets. But if at all applets are required for content delivery, for understanding, for improving the clarity of understanding, then definitely go for it.
Okay, anything else, sir? Last 2 minutes for the session. Any precautions we need to take?
Yeah, the precautions that we need to take is one thing what we need to do is when you're going to create your own applet, make sure that you have a solid understanding of GeoGebra. Okay, for that, as I said, the past sessions in this channel can be made use of. There are a lot of resources to study GeoGebra also in the internet available. Lot of tutorials are there, lot of manuals are there, everything is there. Okay, so these can be used. Even you can use this in your mobile phones. There is an applet to be app to be downloaded in your mobile phone. We always confuse between applet and app.
Yes.
So there is an app that for GeoGebra that is available, which can be downloaded. And you can do it in your smartphone also. Okay. And one more thing you need to keep in mind is that you may get errors in between. Whenever you're creating this applet, you'll get errors, obviously. Okay. Because nobody is going to teach you all these things. You'll have to learn by yourself. Now, when you are getting errors, there are a lot of platforms available to clarify your doubts. Okay, those platforms are like Stack Exchange. There is a platform called Stack Exchange where you can post your doubts, where you can post your errors, and you can get help from a community of people. There are a lot of people working in GeoGebra, and they are constantly communicating among them. Okay, it's not just a single man's effort. Even though this was started by Marcus Hohenwater, okay, he was the person who made the GeoGebra for the first time. Then after that, many developers around the world are utilizing their time to make this more and more beautiful. Okay,
Yes, yes, that's true.
so
And
yeah.
today it is a very useful tool. We have done a few sessions on GeoGebra and we understand its applications very clearly. Thank you so much, Sukeshji, for joining us for this session.
Thank you so much. Thank you.
That's all for this session. For today's webinar, we'll be back with another ICT tool, very important and innovative for you tomorrow at 4 p.m. But right now, it's time to say goodbye. And after a couple of minutes, we'll be back with our Sahyog session, where we are going to talk about how to deal with depression in these tough times. Stay tuned. Namaskar.